Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thanks to everyone for coming to the talk. So today we have Professor James Planck from University of Tennessee. Professor Planck will be visiting us for 2 days, today and tomorrow. So after talk, if you want to meet with him, please feel free to send an email to me. So Professor Planck got his BS from Yale University and a PhD from Princeton University. So after that, he has been with the University of Tennessee, and currently he is a professor in the EECS department. And Professor Planck has been working extensively in a lot of areas, for example, fault tolerance and wide area networks, as well as most recently, erasure coding for storage. And we have been trying to invite him over for years, and finally he's here. So without further ado, let's hear Professor's talk.
All right. Thanks, Jane. All right. Thank you all. All right. I'm going to launch right into this. This is work that I've been doing basically for the past 6 months or so. It's kind of a area that I've been very interested in, and it evolved from Katie Schumann, these are 2 undergrads. I actually like to do research with undergraduates at Tennessee because I find they're actually smarter than graduate students. And they're a little more raw, but they're usually a lot smarter. And so this actually came from Katie Schumann's summer research project that she turned into her math honors thesis, and then basically it got me jazzed up to work on it, and so then that's what I've been doing. And then another student, Devin, who worked with me last summer, but who's now at Utah. So probably shouldn't need to motivate this too much for you all, but the work I've been doing is in the last 6 or 7 years has all been erasure coding, and basically for storage systems like RAID systems where you need to protect your data from 1 or 2 or 3 or 4 or 5 disk drives failing. So you're going to be encoding your data onto decoding devices, and then when they fail, you're going to decode. And I'm going to focus today's talk on this operation pretty much exclusively. So at the heart of erasure codes that are more complex than your standard smaller RAID 6 codes, but even some RAID 6 codes, is this matrix vector product that you use for encoding. Typically, this is a Reed-Solomon code. I give this example. This is an example from a disk company, CleverSafe in Chicago. This is the exact code and the exact parameters that they export in their commercial system, which is they take their data and they carve it up into 10 strips. And then from those 10 strips, they apply a matrix to it and they encode it into 6 extra coding strips. And then they're going to store each of the 16 strips on a different device, typically with their systems across a decently wide area, so that they only need 10 of the 16 strips in order to get their data back. And so the coding operation is described by a binary matrix vector product where your data strips, or all of your strips, are decomposed into the smaller chunks, which sometimes are called packets. But these are treated like single bits in a system. And then you apply a matrix to it. So for example, the first coding bit is going to equal this dot product of this top row of the matrix and the data strips. And since these are all 0s and 1s, what this turns into is a sequence of XOR operations where every green bit is going to identify a data strip that needs to be XORed to make that coding strip. Okay? It's the fundamental operation. So this matrix here is, so you're going to decompose this into, it's called a word size W. So this matrix is going to be composed of 10 major pieces, which are kind of the heavily shaded blocks. And then inside here, each piece is broken up into 8 pieces because it splits up nicely when you break it up into 8 pieces. So this matrix is a 48 by 60 matrix. Okay, because it's 6 times 8 and 10 times. So 48 by 80. Okay. So looking at it, naturally you'd say the performance would be roughly related to the number of ones in this matrix, because each one kind of represents an XOR. But you can do better. Okay? So if you take a smaller example, here's a smaller example of a 4 by 6 matrix, and now everything's a bit, and I'm going to be talking about bits now. But you got to think this stands for a much bigger piece. Right? These are going to be big regions XORed together. So, and the plus operation is going to be the XOR operation. So each row of the matrix represents a dot product, which I have identified there by the equations. And if you do them individually, that's going to equal 12 XOR operations. However, if you note there are common sub-expressions, there are common regions of this matrix that if you pre-calculate them and then use those to calculate the final products, then you reduce the number of XOR operations from, in this case, 12 to 7. Additionally, since we're dealing with zeros and ones, we have this awesome property that 1 plus 1 equals 0. And because 1 plus 1 equals 0, you have additional things that you can do. So in this example, the last two rows, if you add them, they equal the first row. So if you calculate this sum, then calculate these 3 rows, and then use the last 2 rows to calculate the first row, you actually get 1 fewer XOR, and you can do this in 6. So this is the kind of the fundamental observation behind this work. And so the problem that we're working on is we want to calculate AX equals B, binary, with the fewest number of XOR operations. And we're going to make some assumptions. And these assumptions help. Basically, they're assumptions that I'm making now so I can do the work, and then we'll work on them later. Okay, so I'm assuming infinite extra memory. I'm going to be using temporary storage. I'd like to be able to minimize it in practice, but for right now, I'm not worrying about it. Okay, I can calculate the dot products in any order, and I don't think that's really a limiting assumption. And the running time of my calculation of how to do this doesn't matter, because these systems are finite, and if I'm dealing with a code that has 10 pieces of data and 6 pieces of coding, I can store my XOR schedule in a fairly small amount of memory. So I don't mind taking a week to calculate each decoding scenario because there are a limited number of those and I can store them. Okay, the way I'm going to represent this, so now I'm going to call this a schedule. I'm scheduling a matrix vector product. And the way I represent a schedule is, and the way you'll see it throughout this talk, is in the following manner. So I'm calling a schedule an ordered set of C-bit words where C is the number of columns in the matrix. So this is the example. This is a schedule for the example that I had up there earlier, the smaller example. What my schedule is composed of is, first it's going to be composed of a representation of the data bits. So the first C rows are going to be the data bits of the matrix. It's going to look like a little identity matrix, but basically each row represents one of those bits of data. After the Cth row, every subsequent row now has to be the sum of 2 rows before it. Okay? And that way, it's clear that if you define a schedule in this way, I don't tell you how to do the XORs, but it's clear that you can do the XORs, and that basically each one of these is going to represent an XOR operation. And what I want to do is end up with the data. Or end up with my coding product bits in any order. Okay, so the size of the schedule shows how many XOR operations there are. Okay. Now, since the top is going to be an identity matrix, we don't need to look at it. That's going to be implicit in all the diagrams that I show. You won't see the identity matrix. Plus, where I have, this is going to be one of the rows of my target matrix, so I call these target rows. Okay. So my goal in all of this now is, given an R by C matrix, bit matrix, I want to find a schedule that contains all the rows of that matrix, and the size of that schedule is minimized. So that's my problem that I'm trying to solve. Okay? Now, there has been previous work on this. There's a FAST paper by Jim Hafner et al. That has this awful name of code-specific hybrid reconstruction that has absolutely no meaning to me whatsoever. Okay? But it was published in 2004. It's been implemented in an Erasure coding library that I've written. It's very simple, and it's elegant. It's a nice thing. There's another piece of work that people in this room did in 2007 that they published in an information theory workshop. And I'm going to call it sub-X because really what it does is it tries to find common sub-expressions. In fact, this work, I believe you could port straight to a compiler and it would work. It doesn't take advantage of the fact that 1 + 1 = 0. It actually would apply to any matrix vector product that would have common sub-expressions in it. Okay? But I'm going to call it sub-X because that's what it does. And I didn't find an implementation. Cheng told me there wasn't an implementation, so there you have it. There is now. Okay, so what I'm going to show you in today's talk, all this gets around to my finally what I'm going to show you, is I'm going to show you a couple things. One, I'm going to show how previous work fares in the places where we can determine optimal schedules. So for small matrices, you can use enumeration and you can figure out what the optimal schedule is going to be. I'm going to see how close these heuristics come. And then I'm going to talk about two new heuristics, which are kind of augmentations of previous heuristics that the goal of them is to improve the state of the art. And I have one that I call Uber CSHR, which is an augmentation of that original algorithm, and then another one which I call X-Sets. And basically, this defines a framework in which sub-X can exist, but a framework that I can parameterize to try to improve it. Okay. Then I'm going to say how all those work. And then I'll evaluate those on some real-life coding scenarios that would make use of them. I'll discuss their implementation, and then I'll talk about why the paper that I wrote just got rejected from FAST. So you get a little soul-searching in me. Either a little soul-searching or perhaps a little anger. Well, there might be a little mixture of the both, of the two. Okay, so we'll dive right in. The first thing, this was Katie's summer research project that she did. When she was a junior. You got to like this. A junior from rural Harriman, Tennessee, who had not taken math beyond calculus, was able to whip this out in the summer. Very impressive. I mean, she's a great student. So what she did was we wanted to enumerate the best schedules. So given a matrix, obviously, you can enumerate them. You can turn it into a breadth-first search where your XOR operations are edges in a graph. And then you can do a breadth-first search to find the shortest path to your goal. Problem is that's exponential. And so whenever you have an exponential, you got to figure out how to prune it. Well, there's some ways to prune it. I'm not going to talk about how to prune it, but there are ways to prune the search. And then once you prune it, and with a breadth-first search, when the exponential hits you, it hits you in memory more than it hits you in time, because your breadth is so wide you have to keep a queue of everything that you're going to be searching. And so what Katie did was she would measure when memory starts to be a problem, and then when she realized that memory is a problem, she would turn the breadth-first search into a depth-first search, where you might be searching longer paths than you need to, but you can use that to prune. And basically, you enumerate more, but you can find the answer and you don't kill memory. So it's a nice piece of work that she did. And what we did was we evaluated these on square Cauchy matrices that were 5x5, 6x6, 7x7, and 8x8. Now, why do we focus on those? Those are the matrices that build up Reed-Solomon codes. They're small components. That big matrix that I showed you earlier, which you'll see again, which was basically a 6x8 matrix of 8x8 submatrices. Those 8x8 submatrices are these guys. Okay, so they were the subparts that we evaluated. And they were the ones that we could get the running time in so that we could finish the evaluation. And what you see in this is that the two optimizations, well, Cheng should be happy. His beat Jim's. Sorry, in all cases, his beat Jim's, so that's good. But doing the optimization clearly is better than not doing the optimization. And I think when people see these graphs, they tend to discount this bar. This is the bar that if you just do the dot products, you just process the matrix. Most people ignore this bar because they're like, well, who would do that? Well, actually, a lot of people do it. Most implementations of Reed-Solomon coding in this way do exactly this. When I went to CleverSafe, they were doing this in Java, right? And I can't believe they were trying to sell a product on it, but fortunately, it was fast enough for them. Okay? But none of these guys reach optimal. And of course, the gap expands as the matrix gets bigger. So what this meant to me was, it's worthwhile trying to improve this. That was the end goal I got out of this. Now, you could use these results, right? You could take this CleverSafe example, and since I now know an optimal way to schedule each one of these submatrices, I can glue them together and come up with a scheduling of this gigantic matrix, which ends up improving the performance. If this matrix takes roughly 2,000 XORs when you're doing it naively, if you use the optimal schedules, you can drop that down to 1210, which is significant, but we can do better. Okay, I'm going to teach you code-specific hybrid reconstruction because it's so simple. And in fact, when I was doing RAID 6 coding, I actually came up with this independently and published it, and no one knew to say that it had been published before until I went and gave the talk, and Jim came up and he's like, oh, by the way, you might want to look at this paper. And he was right. So it's his algorithm, but it really is a simple algorithm. All it is, it's a greedy algorithm, and it says, all right, what I'm going to do is I'm going to keep track of the number of XORs it's going to take for me to calculate each one of these target rows. And that's going to start with the number of ones in the matrix. And then what I'm going to do is I'm going to choose the one that's the smallest, and I'm going to calculate that one first. Once I calculate it, I now have an alternative for each other row, as I can say, I can either calculate that row just from the data, or I can start from this new product, and I can XOR things out of it and into it, and maybe that's going to improve the number of XORs that I have. Okay? So I'll give an example. Now this example is going to be throughout the talk. I call it C40. It's the Cauchy matrix for the value 40. That's 40 in binary if you flip it around. Okay? And this is the matrix that comes from 40, which is if you are using a 6x6 Cauchy space. It's a nice example matrix because it's got some of the properties that make all of my algorithms look good. Okay. So you start off, right, this row is going to take 1 XOR, this is going to take 3, 3, 3, 2, 2, right, because of the ones in the matrix. Okay. And that's if you're encoding it from scratch. And what you do is you're going to calculate the first row, the smallest, the one that takes the fewest number of XORs, which is the top one. And then what you see is that if I use that row to encode this row, I save myself an XOR, because I can take that and XOR him 2 more bits. And so that improves me by 1. And that also gives me, now I can choose any of those 3 to do next. If I choose B1 next, then I'm going to go ahead and calculate it with 2 XORs. And then I see that if I start with that one, now I can encode this one with just 2. And so it works in that way. Nice, simple algorithm, very easy to implement. Okay, so if you use this to encode, there's the final schedule for that matrix, which takes 11 XORs rather than 14. So you've saved 3 XOR operations. And this technique has been shown that there's some RAID 6 codes that work really well with this technique. And without it, you would not be able to use those codes for decoding, because it would just take too much. There'd be too much overhead. The matrices are too dense. And so that's a nice thing. Now, making this bigger, basically we parameterize this in 2 ways. And they're kind of 2 obvious ways, but we call it Uber CSHR. Basically, take a German word on a meaningless acronym, and then you put it together, and you get a Uber meaningless acronym. Okay, I'm going to parameterize it in 2 ways. The first one is very simple. I just call it a parameter T versus I, which says I can either use target rows only as starting points for improving the number of XORs, or I can use every single intermediate sum. So as originally specified, CSHR says I can start with this one and try to figure out if it improves XORs, or this one, or this one, or this one. Well, I've got an intermediate sum in here. Why can't I check this one to make it see if that improves things? That's the T or I parameter. The L parameter says, rather than just considering starting from 1 row, why don't I look at all combinations of 2 rows, or all combinations of 3 rows? And it may be that if I combine 2 rows together, sure, that's an XOR, but that might reduce the number of XORs in total that it's going to take for me to calculate one of my targets. Let's try that. So the original code-specific hybrid reconstruction only considered targets, and the level is 1, because you only consider 1 combination. So for example, if you bump that up with this example matrix, if you consider intermediates and consider all combinations of 2 intermediate sums, you get the realization that this sum, this element and that element, when summed together, equal that target. And when this element and that element are summed together, it equals that target, and you've saved yourself 2 XOR operations. Okay? In fact, that's an optimal schedule for this matrix, which gives you 9. So that's the basic thing of beefing up CSHR. Now, the running time, it's going to get you. It's exponential. These things are all going to be exponential. It's exponential basically in L, the number of levels. And right, when it's T, it's the number of rows of the matrix that you're worried about. If it's I, it's the size of the schedule that you're worried about. So it's going to blow up in 2 dimensions. But, again, these are things that you can do ahead of time because you have a finite number of cases. So it might not be worth spending some exponentials on it. OK, that was the first heuristic. The second heuristics, you got to take a deep breath because the second heuristic's harder than the first heuristic. All right? The second heuristic associates a data structure, which I call an XOR set, with every element of my schedule every element of my target matrix that hasn't been calculated yet. And what an X-set is it's going to be a set of elements that are already in your schedule. Now, when you start, the data is already in your schedule. So all these X's are already in your schedule. It's going to be a set of elements that are already in your schedule that sum up to equal the row. And you might have more than one of these. When you start off with, there's just one. It's just the data, right? X1 and X3 equal B0, right? This one equals the sum of these 4. But we might augment it and add more of these guys that'll give us more alternatives. So you start with this X set, and then when you add a row to the schedule, the first thing you do is you see whether or not that row is the sum of any 2 elements in an X set, and if so, you replace them by the sum, because that's going to save you an XOR. So, for example, if you schedule the top row, then you note, same savings as in the previous example, that you can now replace the X1 and X3 by B0, and that's going to save you an XOR, which is nice. Okay. And then the goal is going to be to try to use intermediate sums that are going to that are going to shrink as many X sets as possible, right? And this is exactly what Cheng's work was doing a couple years ago. It is the exact same thing. Okay, it didn't work in this framework, but it's the exact same goal. Okay, so to that, I'm going to add 3 parameters to be able to enrich this. The first parameter is what I call threshold, and threshold says, if I can generate an alternative X set within whose size is within a certain threshold of the minimum size X set here, then I'm going to add that to my set of X sets. And best explained with an example. Here, if I set my threshold equal to 1, I'll note that I can create this row of the matrix starting with that sum, and then I'm going to XOR out this piece of data and XOR in these 3, right? So 1, 2, 3, 4 plus that. And now I've created an X set whose size is 1 greater than this. But I'm going to add it to my set. And I can do that with these 3 rows. I can't do it with this row because it doesn't contain either of those bits. So you'd have to XOR all those out and all those in. My X set size would be way too big. So I don't add that. OK, that gives me more possibilities for common sub-expressions. Basically, it gives me more flexibility. Okay, and we'll see a little bit how that works. The second parameter is much like the level parameter before. In fact, I should call it, it's the same thing, so I should call it, but I haven't. When I rewrite the paper, I will. Okay. What it says is it's the same thing as the level parameter before. When I add an element to the schedule, now instead of seeing if I can just shrink the X set using that one element of the schedule, I'm going to look at combinations of elements, of end start elements, and maybe if I use a combination of those, I can add an extra X set that is within the same threshold. Now in this example, I have my threshold equals 0, so all my X sets have to be the same size. Right? And when I add a new element to the schedule, which I believe I do here, you will note, because I'm going to tell you, I'm imagining you're not looking at this and figuring it out, but you'll note that if I take these 2 rows, add them together, and then add in X5, I get this target row. And that gives me an extra X set of the same size that I can add to the schedule. And the cool part about that is I've just added a common sum, which means I've just shrunk down, I saved myself an XOR. Okay, That was 2 of the 3 parameters. The third parameter is the one that you're just beating around your head trying to figure out how to get right. And that is, I'm doing a greedy scheduling algorithm where each step is me choosing which XOR to do next. How do I do it? Okay. So we evaluated about 10 or 15 of these. I'm just giving you the ones that seem to work fairly well. Actually, this one doesn't work well, but it's the one that I use to explain everything. So this is how do you choose the next element. So with max weight, you can say every possible XOR that I can do is going to shrink some number of X-sets. I want to find the element that shrinks the most number of X-sets. Now, there might be multiple ones of those. Those are ones that I'm going to say have maximum weight. And I stole that from you, because in your paper, you converted those into a graph, and then you weighted the edges with basically how many X-sets they shrink. And so those are the edges of maximum weight. So the max weight strategy just says choose one with maximum weight. I don't care which one, just find one and choose it. The sub-X, which is Cheng's paper, converts those into a graph and then uses Edmonds' general matching algorithm to find a maximal matching of those edges because they don't conflict with each other. Basically, that's how you find the most edges or the most number of XORs that will shrink the most number of X-sets, and you do all of those. Okay, so that's what sub-X is. And as I said to Cheng, Edmonds' general matching algorithm, I don't know if anyone has implemented that. It's a bitch. That's a difficult. I bet even Edmonds didn't implement that matching algorithm. Right? He's a theoretician. He just wrote it up and said, isn't this cool? This one, which I think I probably ought to rename, basically says, all right, I'm not going to choose I'm not going to choose XORs with maximal weight. Instead, I'm going to find the smallest set. I'm going to find the target that's the closest to being calculated, and I'm going to choose my XOR from that set. And I'm going to choose the XOR from that set that's going to shrink the most X-sets. So it's kind of like doing code-specific hybrid reconstruction because you're trying to find the closest target, but then since that gives you a range of XORs that you could do, choose the one that's going to increase the most sets. And then lastly, I have MW squared, which basically says you're going to have these 3 all say you have a certain number of XORs that you can do that have maximal weight, right? This one chooses a matching to do it. This one says I'm going to do it randomly. This one says let's just do all of them, and then do a step of a look ahead, and let's just rank. Let's put a ranking on the result and choose the best one. So this one's super expensive, right? But obviously, you're trying to, well, you're doing heuristics. Okay, there's also another one. I got the framework let me write a theorem, and I like writing theorems because I can put little boxes after them. It makes me feel smart. This theorem says, if I'm gonna do an XOR anyway, and let's just say, here's a schedule. This is the sum of this row and the data. I can move it right after this row. I can prove that any schedule that has this element in it, but it's further down than the XORs, I can move it up. What this theorem lets you do is it says, if I got a target that's 1 XOR away, I can prove to you that I can do that target now, and any optimal schedule is going to be equivalent to that. It's nice. Anytime I can prove that I can do this XOR, I should, because it saves me work. And so I put that one in there as well. All right, so that's the algorithm. None of them are really rocket science, but it's just a way that you can parameterize a big exponential search and try to prune it down. So now I'm going to give you a couple of evaluations. This is the first evaluation. It was part of Katie's enumeration. This is just the 8x8 cases, and I just draw them out because I know people like to look at something when I'm talking, and it looks impressive. But these are all the 8x8 matrices that can be used in Cauchy coding. And so what Katie's work did was to find out all the optimal schedules for all these matrices. Okay? And then we compare them to all of our heuristics. And so here's how the heuristics work in terms of average XORs per schedule. So the optimal one is down here. There's none if you don't do anything here. These are all the code-specific hybrid reconstruction ones with different parameterizations. And then these are all of the X-set ones with sub x being here and then the other ones. There's some here that I didn't explain, but they never matter anyway, and I just lifted the graph from the paper, so just ignore those. So the first thing to note is that not doing any scheduling is a killer. I mean, it's factor of 2, worse than optimal. So it's something you definitely want to do. The previously published heuristics are all the worst of their sets. So what it means is the additional parameterization actually does help. In the CSHRs, these kind of steps, which I can't explain. I wish I could explain, but I can't explain them. But what it does show is that each of these parameters does have an impact, right? Considering intermediates rather than considering just the targets definitely improves things, and bumping up the level improves things, although it's kind of minor. Now, of the other heuristics, this one that kind of blends code-specific hybrid reconstruction with the X-Sets wins by a very small margin. Okay? But it is interesting that it wins, and it beats the look-ahead. It beats the heavyweight one, which is impressive. Yeah.
So how much time did it take to compute the optimal?
The optimal for that project took about 5 days. Actually, it took her longer. The first time she did it, it took her about a month and a half. There were like 4 matrices that were just killing her, and that was because she was getting killed with memory. And so she had to put that depth first search in, and then that would take like 5 or 6 days. And then, of course, it was on lab machines, and students who were like, "What's that process?" And they'd hit the power button, and then it was one of those things. When I rewrote her enumeration, and I was able to do it all with a breadth first search. I didn't have to do the depth first search. I pruned it better than she did, and it took me about, I think on this machine, about 2 days. So I could bump it up to 9 by 9. I don't think I could bump it up to 10 by 10.
Is this schedule used for both decoding and encoding?
Yes. Well, it's so okay. In this, so I'll talk about it later. We'll go back to it. Okay, this is just for those little 8 by 8 matrices. Okay, second evaluation. Now I'm going to go to a real situation. Instead of looking at little matrices where I know optimal, I'm going to take a situation that will come up in real life and see if it improves things. So the code I'm using here is a RAID 6 code called the Blum-Roth code, which is it's a RAID 6 code that has really nice properties that does get used in practice in certain installations. And what I'm doing is I'm encoding with the Blum-Roth code. You don't get any schedules. It's a matrix with a provable minimum number of 1s in it, and so you don't need any schedule. You just rendering the matrix vector product is optimal. However, the decoding of this generates very dense matrices. And so you need some scheduling. And so what most installations do is they use code-specific hybrid reconstruction because, I don't have the none up here. I should have the none. The none is way up there. I mean, it's like a factor of 17. It's huge. Okay? So what I did is I took all the decoding scenarios of 2 failures in this situation, which would result in 32 by 128 matrices. They're pretty big, okay, and then applied all the scheduling algorithms on them. And what you get with this is that it's interesting because these guys, on the whole, perform better than these guys. And part of the reason for that is that these, I'm sure it comes from the structure of the code, which I don't understand. I'm guessing no one understands it, but that the rows are related to each other in some way, that doing this thing of building your decoding schedule from another row works pretty well. And you'll note this is the blending of this and the X-Sets, and I guess the structure of these codes lends this methodology well, but this evaluates a whole lot more stuff with it. And that's why this heuristic seems to perform the best. Now, I got the running times here of how long on average, how long it takes to generate one of these schedules. And it's kind of, to me, it's kind of a red herring, I think, because I don't think you're ever going to do it live. You're always going to do this. You're going to pre-calculate this. So the fact that it takes an hour is not a problem. But that's how long each of these guys takes. Okay. So yeah, I have I'm not sure what those circles say. Anything, I mean, circles just say look here, but you were looking there already. All right, if we want to just take a look at running time, just because we're scientists, this takes a look at the running time. So I'm taking this. This is the X-Set heuristic that's like code-specific hybrid reconstruction. And what I'm showing is I'm varying the threshold, and I'm varying end start with the different lines. And end start's the one that hits the combinatorics more than the threshold does. And what you get is, that the combinatorics hit you in running time more than the threshold does, because the threshold is more of a smaller rate. And the schedules that you get, what's interesting is the threshold doesn't matter that much. Now, I don't know if I can prove that or not, but definitely the combinatorics help you much more than the threshold does. Okay? And I don't like this graph. I'm not even going to bother showing it. So I'm not going to show it. I'll just move on to number 3. So evaluation number 3 is that CleverSafe code. Okay, another code that gets used. This one not only, the Blom-Roth code, I can document that people are using the Blom-Roth code because they email me and tell me. So I've been telling Cheng, I would love for Microsoft to tell me what code they're using so I can say, hey, Microsoft uses this code. Okay, but we'll work on that. CleverSafe, even though I signed an NDA with CleverSafe, they don't mind me telling what code they use. So they use this Cauchy-Reed-Solomon code. This exact code is the one that they use. And so I'm working on this code, scheduling it. And now we have 2 extra bars. I have my no scheduling. This is if I use those optimal codes. I use the optimal codes for each 8x8 subpanel. That's what I get from here. And then here's with my scheduling algorithms. And what you get from this is that now the looking for common sub-expressions is very successful in terms of improving the performance, and this code-specific hybrid reconstruction of using our current rows and trying to do this kind of greedy search on it is not nearly as effective as the others. Probing further, that was encoding. That was just encoding that one matrix. Now I'm looking at decoding. And now I'm decoding, and perhaps this isn't overly realistic because I'm decoding from 6 failures. And so you might say, well, when are you ever going to get 6 failures? Well, think of it in a different way. With CleverSafe situation, they have these blocks spread out over the wide area. So it's not that you're getting failures, it's just you're trying to find 10 blocks. Okay? And so now you want to decode from these 10 blocks. And so these are all 10 choose 6 decoding situations. And I chose a threshold of 2, and then I've had end start varying from 1 to 2, and we show the difference in the coding algorithms and the look ahead. What's interesting from this, I find, is that the look ahead wins, and the one that's like code-specific reconstruction loses badly. Well, not badly, that's a small y-axis, but it still loses. So something about the structure of these Cauchy matrices doesn't lend itself well to that decoding methodology. Last graph. What is this one? This one is I am doing a Cauchy-Reed-Solomon coding scenario where here I have, it's going to be a 16-disk system. Here I have 8 data disks and 8 coding disks. There's the CleverSafe. There's 12 data disks, 4 coding disks. And now I am doing encoding. I'm doing decoding from 6 failures. And I'm doing decoding from 4 failures. Sounds to me like I have that wrong. That should be swapped. Yeah, that's why my paper got rejected. Okay, and then these matrices are called original matrices. These are the ones that got used from the original paper that described this coding technique. Cheng's advisor and I wrote a paper in 2006 on how you can use an alternative matrix specification where you get a sparser matrix to do the encoding. And so this shows using those for the encoding and then the decoding. And what you get from this is basically none, the best code-specific hybrid reconstruction, and the best X-set. And basically this graph is just showing, well, it shows to me, it makes a difference. In terms of XOR operations, it makes a significant difference. Choosing a better matrix also definitely helps the encoding situation because you chose a better matrix, but it really doesn't have much impact on decoding. So, I don't know, I find it all interesting. All right, just So that's the evaluation part. We'll talk a little bit about implementation. The CSHR is 400. It's pretty simple. 400 lines of C, and I wrote it badly because it's a memory hog when L gets too high. So I started rewriting it on the plane in C++. I think the plane ride back, I'll finish it, or maybe if I'm bored tonight, I'll finish it. It's what I do in my spare time is code. So I'll get that one done. The X-Set one is much longer because I had to implement that stupid Edmonds general matching algorithm, which is hard. That's a lot of the 1,700 lines. And also, you're keeping track of a lot of stuff with that X-Set stuff. So that's about 700 lines. It's a memory hog when the threshold gets too big because you have to keep around all those extra X-Sets. There's no real way to reduce that. So that's when it starts blowing up in memory. They both spit out schedules. I'm going to talk a little bit about this, about the fact that just spitting out schedules isn't everything. And I'm going to get these guys posted online in the next month. I'll pop I'm not sure which license I'm going to pop on. I'm not going to use the GLPL anymore, but I'll pop a license on them and put them out there so that anyone who wants them can make use of them. You just throw some zeros and ones at them, and it'll throw some zeros and ones back, okay, which is nice. Okay, I will put them into JRacer. JRacer is my open source erasure coding library. It's been around for about 3 years. A lot of people use it. I mean, I've got a wonderful laundry list of companies. Microsoft will be one of them. I've had people tell me they use it. If they tell me to use it, I'm happy to say it. So HP, Microsoft, BitTorrent, IBM, they all, and then laundry list of universities all use JRacer. Usually, they're not using it in their products, but they use it as a starting point. If you're doing a product, they use it as a starting point, and then they make it better, which is fine with me. The biggest challenge of putting this into JRacer is I've got this memory problem that I have all these intermediates, and I assumed infinite memory. But where do the intermediates go? You got to store them somehow. Can you minimize the memory footprint? Now, that example's too easy, but when you're spitting out a schedule that has 700 XORs in it and you have 48 targets, that's a lot of extra memory. And figuring out how to reduce that memory is tough. I'm going to work on it. I've done some work on it. And you turn it into a graph, and you do a topological sort of the graph, and you do some other stuff. But I haven't formalized that yet. But that's good. That's the biggest challenge in getting this into the erasure coding library, is that I got to figure out how to do it. Okay. Finally, so I wrote all this up. Paper was rejected from FAST 2 weeks ago. Devastated I was. I submitted 2 papers to FAST, one good, this one, and one bad with CleverSafe, and the CleverSafe one got in, and this one didn't. And if you want me to talk about the CleverSafe result because everyone else cares about it, I will. But it's not mine. It's someone else's, and I did the work with them. But go over. You have to do a little soul searching on why it didn't get in. And I always have to put these up because you're thinking of it anyway. First reason it didn't get in is it focuses solely on reducing XOR operations, which is nice because I can focus on it. It's an open problem, and I can focus on it. But CPUs are fast and disks are slow, and our CPUs are no longer nice, beautiful RISC machines that you can reason about, but they're these big, junky, awful things that you can't reason about, and you got to use vtrace to figure out anything. And turning that into a nice, elegant problem is something I can't do. Right? And so all of these things aren't addressed by my work. And so I got the line, you should have implemented it to show this magnificent, put it in a real system, and I thought, oh, screw you. But okay, there it is. That's the main reason it got knocked out. I had too much math in the paper. Hakeem Weatherspoon told me this rule. I had to look it up to find that it came from Stephen Hawking, which says every equation kills half of your audience. Right? So, if my audience started off as 1, then when my paper was done, I think I had 2 to the negative 32 or something, like people left. So, and I hope I'm not losing you with that, but, hopefully you all understand that. So that was a problem. Someone told me I should have submitted to the information theory workshop, and I'm like, no, not that. No one reads that, right? Or the only people who read that are other eggheads. So that was a problem. Third problem was they said the improvement was incremental, right? There's previous work, there's me. There's previous work, and there's me. And that's not significant enough for them. So reasonable. And then finally, no one on the FAST PC cared except for me, but I was kicked out, so I couldn't argue for my own paper, so it didn't get in. So, oh, that's right. No, my other talk I had it there. So the plan, here's my research plan for the next little while. I'm going to be resubmitting it to DSN. I'm going to post those guys online so that anyone who wants to use them can do them, and I might have a usage case. I I might put the Clever Safe code and actually put a performance evaluation, real live performance evaluation on it to show that it matters. I probably won't. I probably should. If I'm resubmitting it to FAST, I will. But DSN's deadline is like 3 weeks, and so I'm not going to do that. I'm going to implement it within JRacer. I say write up the whole mess because I got to solve the temporary memory problem before I do that, and that's a very hard problem. And so I'll write that up, but and I'll probably submit that to SP&E because it really is a software thing. And I like SP&E, even though academics don't. I think SP&E is a nice journal. SP&E, you don't need to actually have a new research result. So the paper of mine that has the most citations by far is a tutorial I published in SP&E that had 0 research contribution and that everyone in the world loves. So I love this journal for that reason. Okay, I'm going to dabble with the 5-page of the information theory workshop that I'm going to talk with Cheng about, but he says he's not an information theorist, so now I got to talk to an information theorist. Maybe I'll talk to your advisor. Maybe I'll talk to his advisor and figure out, because I've got a cool result in here. I'll tell you, since none of y'all are going to steal this idea. Don't steal this idea. Everyone thinks the lower bound, I think, the lower bound on doing a Reed-Solomon code or any erasure code that's significant is going to take at least, if I have k pieces of data, the lower bound on encoding is going to be k minus 1 XOR operations. It seems like you shouldn't be able to get lower than that lower bound. I can. Using these techniques, I can actually, I've found Reed-Solomon codes that I can encode with fewer than that number of XOR operations. I think it's stunning. It's completely counterintuitive, and I've double-checked it. So, but I don't know where to publish it. Obviously, I can't publish it in FAST. They don't even care about this stuff. Right? So I got to publish this with...
I didn't hear clearly the result, basically.
Here, let me get a matrix for you. Let me get that Clever Safe. I've used this picture a lot. Okay. Call this K. Okay? I have K pieces of data. I want to encode it into 6 pieces of data. One would think that the lower bound on computing this would be k minus 1 XOR operations, because you got k pieces of data. How could you have fewer than k minus 1 XOR operations per piece of coding data? Okay, so you look at any RAID 6 code that you make use of, like RDP and even odd. RDP hits k minus 1 XOR operations. Parity, RAID 5, strict parity is exactly k minus 1 XOR operations. Right? You can't imagine you could do parity in less, because if you're using less, you're missing the data. Well, I can come up with a situation where I take a Cauchy Reed-Solomon coding matrix, apply my scheduling optimization to it, and I get fewer than k minus 1 XOR operations on average. Now, the on average is the key part, but to me, I thought it was a lower bound. Or I really did think it was a lower bound. And it's...
XOR code is actually at k minus 1, am I right?
No, his is a little bigger, because you got to calculate the adjuster. If you didn't calculate the adjuster, it would hit it exactly.
Yeah,
okay, RDP hits it exactly. Okay, and there are a couple. The Xcode hits it exactly. There's some, but that's always been cited, but it's not. And I don't think I'm wrong, and I don't understand why. And I think some people should be jumping up and down saying, "Damn, this is cool." But I got to figure out who's going to be the audience who's going to look at me and say, "Hey, that is cool." So don't steal it, all right? But that's my information theory workshop paper, which. Sorry if I'm running a little long. I don't know how long. I thought you said 45 minutes to an hour, so I'm good. All right, I'm not boring my audience too much yet. All right, well, let's go back. That's right. Now, internally in Microsoft, everyone's seen it. Don't steal that result, all right? Where's my camera? All right. Yeah, they do. Y'all don't steal my result, because it's cool. If you do, you better cite me. I'm going to be mad. All right, where's my plan? We're on to that. Oh, and then this, and this is one of the things I would love to get out of being here, is this problem that processor architectures are no longer what they used to be. I don't know if we get mad at Intel or Moore's Law or transistors or what, but we've lost the nice RISC world we used to live in, and we are in a complex world that is very difficult to reason about. And I would like to be able to figure out how to reason about it and to figure out how that applies to erasure codes. And I'm, even though I'm a systems guy, I am not good at that at this point because I haven't spent too much time beating on it. So I would love to hear ideas of how we can lay out the problem so that we can design our erasure codes so that they have maximum impact. And so I will be working on that at some point. I wasn't funded to work on it, but I will work on it. Okay, so finally, conclusions. Framed the problem, gave you 2 sets of heuristics that are ready for implementation. They improve the state of art. I've told you my research plan for the next year like you care. And basically, I'm just going to keep on bridging this gap. It's what I do. I'm a systems guy who likes math. So I'm just going to keep on trying to figure out how to get it better. And that's it. I don't know if we have any questions.
Ken and I have opportunity to talk to you in the afternoon, so I will give time to our rest of our audience.
Okay, and I don't know if I answered your question or not. I think I was trying to. I was punting it later because figuring out those optimal schedules for the little matrices. You can do that in both encoding and decoding, but really you do better when you encode or decode by looking at the whole matrix and considering it as a whole thing that you need to schedule. That's why I put off your question, so hopefully I've answered that now. Yeah.
And is XOR a fair performance metric?
Well, that's...
Would you expect it to differ from the running time around decoding?
That's this problem here. So, all right, here's the issue. Here's how I see. In 2009, I published a paper in FAST where I took JRacer and 2 other open source erasure coding libraries, put them to test on what I considered a realistic and controlled setting for testing their performance. Before all this other mess happened that everyone's talking about processor architectures now, I would always get someone who would raise their hand in the back of the room and who would say, I've got a read-Solomon encoding implementation, general purpose that doesn't use XORs, it uses Galois field arithmetic, that runs at cache line speeds. And because I've got that, everything that you do is meaningless to me. So, of course, I always say, well, would you please give that to me so that I can use it for evaluation? And then they say no, because I work at Data Domain, and I work at HP, and I work at IBM, and no one's going to let me I'm not going to let you see my code. So I tried to do it as best as I could. Now, the end result of that paper was that no read-Solomon coding implementation I could get my hands on that worked using standard Galois field arithmetic even came close to the XOR-based codes. Factor of 4, factor of 3, pretty big factors. Now, I didn't have their codes. Now, and their codes were also just for RAID 6. It wasn't for like the CleverSafe situation. The other result that I got out of that, and I'm going to give you a long answer to a short question, was that the XORs matter. The running times of the code were almost exact matches of the XORs. Not completely, because there were some caching things in there, but they were. Now the problem was I wasn't using the SSE extensions, right? If I had multiple cores, I wasn't making use of them. That's hard. I mean, it's hard to write a general purpose implementation. Now, if I'm a disk company, of course, I'm going to put the 6 months of time into it so that on my architecture, I'm going to squeeze everything out on it. In that, I've been told, and I believe, that if I've got the data sitting there next to my processor, and I've got 2 processors sitting there plus an extra unit that I can use for XORs, then if I arrange my code so that it has 3 XORs, but they all make use of that data, they're going to work exactly the same as 1 XOR. I believe that. So is XORs a fair measure? No, but right now it's the best I've got to be able to evaluate a code. We just wrote a paper in DSN last year. One of his advisor's other students and we wrote a paper basically saying the order in which you do your XORs can impact performance by about 20 to 30%. And so that's the order is probably more important than the XORs themselves. And that's also interesting. The problem is that I'm running up is I can't reason about it. I really would love to be able to reason about it. And the other problem is that it is, well, now this is just me. Y'all are Microsoft. I'm an academic researcher. I can't compete with you when it comes to writing stuff that works fast. I can't. My funding model and my labor model and everything else is such that I can't put 10 people on a code and say, make this fast. So I made a decision last time I applied for funding is that I really need to stay 5 years ahead or 10 years ahead and do things that you all are going to read and then you all implement. And so I need to find fundamental principles. Right now, that's the XOR operation. I don't think that's going to be realistic for much longer, but it's all I got right now. And I hope that doesn't make me sound too unapplied. But as a university researcher, I can't compete. I can't put myself on a playing field with Microsoft, IBM, and HP and think that I can win and have impact.
You want to realize in Microsoft, actually, it's also only one team working on the specific.
Okay, well, okay.
I mean,
so maybe not Microsoft then.
Make program efficient.
Okay.
It's not you can put 10 people on it and make it work.
Okay, maybe IBM's putting 10 people on it, but I mean or maybe data domains putting I'd be breaking an NDA to talk about another company who is putting these people on it. Okay, but it's foolish for me to try to compete with that in my office in Tennessee. I've got to find out. I got to compete on problems that aren't urgent for them there, but are going to be urgent in 2 years, and then they can take my results and make use of it. That's my goal, at least in there. Okay. So again, long answer to a short question, but I think it's a very important question. And as processor architectures have changed, it's a question that has much more pertinence. Yeah?
You mentioned that we can easily pre-compute and save all the combinations before runtime. But, for example, Clever Save, it's 16 pieces.
Mm-hmm.
There seems to be a whole lot of cases to decode, like 1 in 16, 2 in 16, all those combinations. There could be thousands and thousands of them.
Well, 16 choose, or 10 choose 6. I guess it's really 16 choose 6. That's still not that big of a number, right? 16 to the 6th. I guess that's a...
6 is a huge number. You cannot pre-compute all the basically same.
16 choose 6? I don't think it's that bad.
It's bad.
I won't do it. I actually don't. I thought I think I pre-calculated if you do the 10 choose 6, you can store all of those schedules, I think, in under 2 megs. Of all. Now that's not 10 choose 1, 10 choose 2, 10 choose, but 10 choose 6 is going to be bigger than. No, 10 choose 5 is probably bigger. I don't know. I think 10 choose 5 is.
It's feasible,
right.
When you go to 16, it's
right. It's going to be pretty. All right, I'm going to have to. I'll figure it out. Ping me. I'll figure it out. I'll send you an email and say exactly how many. Now, because the other thing about these schedules is they're varies. I mean, if the schedule for the Clever Safe code, the size of the optimal schedule is 700 rows. Now, of those 700 rows, you get to throw away 80 of them because they're identity matrix rows. So we're down to 620 rows. And each one of those rows is 80 bits in length. 80 bits. I mean, you store 80 bits in 10 bytes, right? So 10 bytes times 600 is very small, right? And even you multiply that by 2,000 or 3,000, it's still fitting in a very small amount of memory or a very small amount of storage. It wouldn't even be memory; it'd be in storage. So it's I think it's reasonable to pre-compute it. But I forget which. In my paper, I computed for one of those scenarios, and it came out to like under a meg. So I don't think it's actually that bad. But you're right. I'm cheating a little bit because I'm doing 10 choose 6 rather than 16 choose 6. But no.
Also, sadly, agree with some of the fast reviewers. These Erasure codes are generally implemented in distributed systems, and most of the time is spent in moving the data around rather than computing.
Absolutely. That is true. But, well, yes, I'm just going to say that argument is always going to carry weight. But there is always going to be a significant CPU overhead.
Yeah, I think it's not probably the time savings, but you save power
Right.
by doing less work on the CPU as well.
Right. That's absolutely
This
true.
argument goes away if you're using SSDs, because you want to save in space, so you read some codes, and they're very fast, so you need to do these computations very quickly.
But still, the data comes over the network. Yes, you're right if it's in a single system, but in a single system, you rarely use erasure codes. Erasure codes are more suited if the system is distributed.
It's true. What I need, fair argument. But you could, I mean, I can always come up with the scenarios where they matter. You know, allmydata.com. There's most. I mean, yeah, it's not completely on the critical path. Now, allmydata.com is one of these archiving companies on the internet where I give them my pictures and I want to make sure that my picture, you know, I pay them $5 a month and I want to make sure that I can get all my pictures and videos back. And of course, they won't tell me they can guarantee it because they can't. But it is a company. Now, their business model is actually to use outdated equipment because it's cheap. That is their business model. And so they use Reed-Solomon codes that tolerate, I think, 6 failures in there. And their equipment sucks. So the CPU burden actually does matter. Now, it's hard to sell that to fast, but it's a situation where these guys email me and say, I love your stuff, right? Because the CPU does matter. The CleverSafe folks, it does matter as well. Now, CleverSafe has an academic installation that they're trying to put together. They've been trying to put together for a couple of years. Well, hopefully we'll get it. We'll get 5 places that'll have their actual commercial equipment, which is running their stuff, where I'm going to be able to get the source code and I can do some performance measurements and hopefully be able to demonstrate on commercial hardware that this is another scenario in which it matters. But, yeah, definitely fair argument. Always going to run up against it. I had something else on the tip of my tongue, but I lost it. I'll get it back.
Thank you, speaker again.
Okay, thank you.